So you said we were the part where we are computing the inverse.
Yes, where we are, for instance, if you're given a 3 by 3 matrix, and we're supposed to specifically use Gauss-Jordan method, elimination method.
This is a Gauss-Jordan elimination.
Yes.
Mm.
Yes, there.
So the basic idea is this: you have the following situation. If you have a square matrix which is invertible, what you do is you augment it with the identity matrix on this side. Then you apply some row operations, which will turn this matrix into, you can see what I'm writing on the board.
Yes.
Okay, so it will turn this matrix A to its reduced, we normally call it the RREF, reduced row echelon form. So what it means is at the end of it all, you'll end up with a new set of matrices. This one will be, if it's invertible, it will have been reduced into the identity matrix, and you'll have a new matrix on this side at the end of this process. So once you're done with this process, the matrix you're looking for is the inverse of A, and that inverse would be equal to this new matrix B. So for the sake of brevity, I think, or time, I will use a small example to illustrate this. Suppose we have say a matrix like this. So we need to find the inverse of this. If this is A, of course, it's possible to do this with other techniques, but we want to apply the Gauss-Jordan elimination so that you can see what happens. So what I will do is I will augment this with the identity matrix. So the augmented matrix now will look like this. I will have 1, 0, 2, and 3 as my matrix. On the other end, I put the identity matrix of the same size. So up to this point, I believe it makes sense.
Yes, it does.
Good. So the idea is to turn this matrix on this side into its reduced echelon form. There are a number of operations you can, not so many anyway, since it's just a 2 by 2 matrix. The first row seems to be fine, so we can leave it as it is. That means also the first row on the right-hand side will be left intact. So to turn this into a reduced echelon form, the first thing we'll want to do is to turn this into a 0, right?
Yes.
So which operation will give us 0 there? It will be replace the second row by the sum of itself plus
-1
minus 2 times
-2 times R2, R1.
So what will we have here?
0.
This will be 0.
1.
And this will be? How do you get 1?
No.
You multiply, the first row has 0. If you multiply -2 by 0, you should get 0.
0.
Then if you add
plus
3, you should get 3.
It's 3. It's 3.
So you do the same operation on this side. So this side also benefits from that operation.
Yeah.
So we are multiplying this by 2.
It's 2.
-2 and adding.
-2. It's -2.
And this one will still be 1.
Yeah.
Right?
Yes.
So this side is still not in reduced echelon form.
Yeah.
There's one step missing.
Yeah.
We need these 3 to be a 1, right?
Yes.
So the operation that can do that will be the following. So The first row, we leave it intact. Second row, exactly as it is. And we need to multiply by 1/3 the second row. So the new operation that we'll do is multiply by a scalar to give us 0,
1,
1
negative 2/3,
minus 2/3,
1/3.
1/3.
Oh,
I don't know if that is correct.
yeah. Now it's making sense. Yeah.
So this, if you have done calculation correctly, this matrix you have here is the inverse. The one I've circled,
Yeah.
that becomes your inverse. So this is the same thing you do, even if it's a 10 by 10 matrix, it's the same thing you do.
So you'll always, let's say for instance, by doing step 2, but our it's not still reduced in echelon form. So we'll have to continue till we have this. We have the echelon form.
Yes.
Okay. So
You
you
must
don't
have
stop
this side
until.
in echelon.
Okay.
Yes.
Okay. Thank you.
So the other thing is, if you look at the notes, it says the same thing. You'll only stop when this is the identity matrix.
Yeah.
If the matrix is invertible, the reduced echelon form will just be the identity matrix. So you keep going until you get to that form. There's a lot of theory we've left out, but probably don't need most of it. It will take too long to go through the theory.
Okay. And another question, when we are considering the system of linear equation, is it maybe during a cut, is it a must for us to draw? Let's say we've gotten the variable of x and y. Is it compulsory for us to show it on the x and y axis using a diagram or something? Or so long as we've gotten...
If I give you a problem to solve, it will not be one that you can draw.
Okay.
The 2x2 systems are just there to help you see what is going on, but you will not be getting questions from that are that simple. So if you get any questions, you should be, they'll have more than 2 variables, so you'll not be able to draw.
Okay. Okay, thank you.
Today, I wanted to start on this new topic, linear transformations. Did I set up recording? Let's just confirm. Yeah.
Yeah,
Recording
you
is
did.
on.
There are some guys who are waiting on the lobby to be admitted.
I checked. There are some buttons I'm supposed to press to turn someone into a co-host, but I can't seem to press those buttons. I will have to. I tried to do it at the last minute, just before the class, but I've seen a tutorial somewhere. The tutorial doesn't seem to be helping. I will go back to it later. For now, I think I will have to manually admit people. But I think immediately after this, I will do my research. So today we talk about the linear transformations. I think it might be the only topic we'll cover today. There's one more we can do, the singular value decomposition, but I don't know if we'll have time. So we talk about linear transformations. so far we've been talking about dealing with vector spaces on their own separately. Now we want to see if we can find relationships between different vector spaces. In particular, we shall be focusing on the Euclidean spaces. So the first thing we'll define is a linear transformation. If you have a map from Rm to Rn, I think you're familiar with these Euclidean spaces. If you have a map from Rm to Rn, which satisfies these two properties. Now the vectors are supposed to be bold. Most of it, I will fix that. I was preparing the notes and was planning to come back and make all of them bold, but I did not. Some of them are bold, some are not. These vectors are supposed to be bold, but from the context, you should be able to tell what is a vector and what is not. So is there a question?
No.
Okay, maybe if you don't have a question, it's good to just keep the mic off so that you only switch it on when you have a question. So this map from Rm to Rn will be called a linear transformation if it satisfies these two properties. In other words, the image of the sum of two vectors is the same as the sum of the images of the individual vectors, like that, and the image of a scalar multiple of a vector. There's something missing here. This should be T of V1. So T alpha V1 should be alpha T of V1. So basically what it means is the image of a scalar multiple of a vector will be equal to the same scalar multiple of the image of the vector itself. There's a missing T here. T acting on V1. So let's look at some examples. So here is an example of a map. We take a map that takes a vector in R2, sends it to another vector in R2. And this is how it's defined. It picks a vector XY and it sends it to another vector where the first component is the sum of the two and the second component is a 0. So the plan is to check if this map is a linear transformation. There are two properties you must show. You must show that it satisfies. We'll start with the first one. So we need to pick two vectors from the domain of this map. So we have two vectors from R2, and we need to show that the image of the sum of the two vectors should be equal to the sum of the images of the individual vectors. So let's try to do that. Keep track of what the definition is, and you should be able to apply it. So essentially what this map does, it picks a vector XY and sends it to a new vector where the new vector consists of the sum of the two components in the original vector, and it makes the second component 0. So any vector you give it, this is exactly what it will do. It will add up these two and make the first component of the image and 0 out the second component. So if you add V1 plus V2, you will get, this is a vector you will get x1 plus x2, y1 plus y2. If you apply this map to this vector, it will add up the two x and y coordinates and 0 out the second one. Since these are just addition, this is just addition of numbers, there's no equal sign here. This equal should be out. So this should be, if you split, you can split this to x plus 1 separately, x1 plus y1, and x2 plus y2 separately. And then you can split them into two vectors. And when you do that, you will realize that this one is just the image of the first vector, v1. And this one is the image of the second vector, v2. So we have shown that the image of the sum of two vectors is equal to the sum of the images of the individual vectors separately. So the one thing we need to check now is what happens to the image of a scalar multiple of a vector. Once we check that, then we're in business. So we try to get the image of alpha V1 or the scalar multiple of a vector. So this one, if you multiply V1 by alpha, it's the same as multiplying all the entries of V1 by the same constant alpha. If you apply the same linear map onto this vector, what does it do? It adds up the two coordinates, makes it the first coordinate of the image, and zeroes out the second one. So this is what you'll end up with. Alpha is common here, so I can pull it out, and I can go one step further and pull it out of the vector. It still works. But what is left as a vector here is just the image of V1 from the definition. So I have shown that the image of a scalar multiple of V1 is the same as, is equal to the scalar multiple of the image of a vector. So these are the only two properties we needed to check. And these two will confirm that T is a linear transformation from R2 to R2. So if you look at the definition did not require that these two numbers, M and N, be equal. They can, but they don't have to be. The first case we considered is where they are equal, R2 and R2. They don't have to be equal. We shall see some examples where they are not equal. So are there any questions on that? No. So this is another example, but now we have a map from R3 to R2. So it takes a vector in R3 and sends it to this vector in R2. So what it does is simply picks the first two, adds them, and makes Z, or the third component here, is made the second component in the image. So but now here you end up with a vector in R2, but you started with a vector in R3. So again, the aim is to prove that this is a linear map. To prove that, we need to check those two properties again. So as usual, we need two vectors from R3. So V1 and V2 are vectors from R3. We pick vectors from R3 because R3 is the domain. We have to start with vectors from the domain here. Get the image of the sum of the two vectors. If you add V1 and V2, this is the vector you will get. Apply the map T to this vector. What it does, it adds the X and Y coordinate and makes the Z coordinate the second one here. So that's exactly what we've done. With a bit of manipulation, you can see that this vector can be split into two like that. And that split gives you the image of V1 plus the image of V2, because this is just the image of V1 and this is the image of V2 under this map T. So one property down. The next property is to check that what happens when you have a scalar multiple. So if you have a scalar multiple of V1, that's the scalar multiple of V1. If you apply the image, what do you call it? If you apply the map T on this vector, this is what you will get. Alpha is common, you can pull it out, and you're left with this vector. But this vector is just the image of V1. So we have shown that the image of alpha V1 is the same as alpha multiplied by the image of V1. And then that means we can conclude that T is a linear transformation. Is that clear?
Yes.
So these are some of the properties of linear transformations. We shall not prove them. If you have a linear map from Rm to Rn, the zero vector in Rm will always be mapped onto the zero vector in Rn. This will always be the case for a linear map. The zero vector in Rm will always be mapped onto the zero vector in Rn. So these zeros are not the same. This zero is a zero vector in Rm. It has m components. And on this other end, it's a zero in Rn, which means it has n components in it. So the second one simply means if you get the image of a negative of a vector, it's the same as the negative of the image of the vector. So this one simply extends the idea of scalar multiples. If you get the sum of scalar multiples, you can split it up like this for any finite number of vectors. So you can check some of these properties in your own time. Check with there are proofs for this, but I'm not focusing on the proofs. You can verify using some of the linear maps that we have done before. But this will be true for any linear map. So these properties are true in general. They are not restricted to any specific linear map. It's for all, any linear map will satisfy these properties. So for most of these linear maps, it's possible to represent them as matrices. So that's the next thing we will do. So here, let's consider the linear map from R2 to itself, which takes x, y, and sends it to x minus y. So can anyone guess what this map is? X coordinate does not change, but the y coordinate changes. What map will this be? Can someone guess?
Rotation.
Pardon?
Rotation.
Rotation will not keep the coordinates the same. If you are
Inverse.
doing let's see what a rotation does. If you have a rotation, so if this is the point P, so you rotate it through some angle, if this was XY, the new point for the image, if you call it P prime, will not have the same values. Maybe it will have, so X prime and Y prime will not be the same unless you pick a very specific rotation. But in general, rotations will give you new values. This one, the map we have is, it leaves X intact. So this one is sent to X minus Y. Nobody can guess still.
It's a mirror image on the x-axis.
Okay. So yeah, let's see what happens. So if I have a point here, let's call it XY. So if for me to maintain the same X coordinates, I have to go along a vertical line, right? Otherwise, I will lose the X coordinate. So then I have X on this side and minus Y. So it's a reflection along the, as you said, the reflection along the X-axis. So that's reflections are examples of linear transformations. You did this in high school in a slightly simpler way. And even then, I think you encountered this matrix. So anytime you wanted to do the reflection, you simply multiply it by the matrix. So this matrix has exactly the same impact as this linear transformation. And therefore you can represent that linear transformation using a matrix. There are some tricks on how to do that. We'll get to that shortly. So I hope that makes sense. This simply is to show you that if you have a linear transformation, it's possible to represent it as a matrix, because this linear transformation sends xy to x minus y. If you multiply xy by this matrix, it gives you exactly the same image. So this matrix can replace the linear transformation. So here is another. So here you'll note it was a map from R2 to R2. So that's why you have a square matrix. So here you have a map from R3 to R2, right? So XYZ is sent to this vector in R2. So that's a map from R3 to R2. Now, this matrix has exactly the same impact as a map. So if you multiply this matrix and this vector from R3, you get exactly the same result. So again, here is another example where you can represent a linear map using a matrix. Is that making sense? So the challenge we are going to face now is, how do we find this matrix? Given a linear transformation, how do we find this matrix? So this is what happens. There are two steps. You pick the standard basis. The way we are doing it now, you need to pick the standard basis for the domain. In this case, our domain was R3. So the standard basis for R3 will be these vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. So you get the images of those three vectors. Once you have the images of those three vectors, those images now in the same order will become the columns of your matrix. So for instance, 1, 0 becomes a first column, negative 1, 2 is the second column, and 0, 1 is the third column. So this is a matrix now that will represent this linear transformation, but we have to be careful how we state that. This is with respect to the standard basis. If you don't use the standard basis, it's a little more technical. You'll be working with the coordinates. It's a little more involving. So I left out the examples where you don't use the standard basis. But maybe I can add them in the notes before I share if you need one. Probably not. It's a bit technical. I would have to explain it. Some of you may understand, but it may be new to many of you. So we'll stick to this case where you work with a standard basis, get the matrix. If you have time later on, maybe we can do some examples where you don't work with a standard basis. So I'll leave this, give you some time to do this exercise, maybe about 3 minutes. Remember how this works. You find the image of a standard. Again, here it's a map from R3 to R4, because this vector has 4 components. This one has 3. So this is from R3 to R4. It picks a vector in R3, sends it to a vector in R4. So your challenge is to find a matrix which does the exact same thing to this vector. So is 3 minutes enough? One minute?
Excuse me, sir.
Yes.
Give us 5.
5. Eh?
Yes.
Okay. But remember the process. The process is this. Pick the standard basis for the domain. In this case, again, your domain is R3. Find the images of the elements in the standard basis. Those images become your columns. So just double check that.
Excuse me, sir. Could you go back to the slide, please?
Meet in person, and I go back to the slide. Well, have we managed 5 minutes so far? Have you been able to figure it out?
Yes.
I have.
Okay, that's good. So I assume all of you have figured it out, but the basic idea is to find the images of the standard basis elements in R3. And once you find them, you make them the columns of your matrix. So the next thing we look at is the image of our linear transformation. Maybe it's best if I draw. So I will go to the board again. Suppose I have a map. I have this is my domain. My map is sending RM to Rn. So I'll just make some container here, which will represent Rn, Rm, or my domain, and I will make another container here. So this one picks a vector here and sends it to another vector here, which is the image of V. So our map, we can use the letter T to represent the map. Map is from Rm to Rn. So you can find a smaller subset of Rn. So I'll just shade it. So this turns out to be, if you find the images of everything in Rm, they all end up in this smaller subset. It doesn't have to be smaller, it can be the whole of Rn, but let's assume that that is all there is. So if you get all the images, they all fit in this shaded area. Pick anything in Rm, gets its image, apply the map to it, they all land in this small box, which is part of Rn, not the whole of Rn, but part of it. So this part where they land is what we call the image of the map T. That's the image. So if you are to write it out using the set notation, the image of T in our case will be all vectors, some vectors in this case Rm. No, the image is not in Rm. So let's call it W. It will be all vectors W in Rn, which for which we can find a vector V, which will be mapped onto W, where V is a vector from the domain being Rm. So this gives you the definition of the image. So it's possible for the image to be the whole of, if the image is the whole of Rn, if this happens, it doesn't always happen, but if it happens, then we have a special name for such a map. Such a map is called a surjective linear map. So we shall look at some examples where we have maps that are surjective and some that are not surjective. So given a linear map, we want to be able to describe this image, or at least be able to find a way to describe it fully. So the other thing that we need is this. We know that the image is a subspace. Again, I will not prove this, but it's an important statement. The image is a subspace. Turns out to be a subspace of always. It will always be a subspace of the core domain In this case, our codomain is Rn. So as a subset of Rn, it will be a subspace. So this is a subspace. It can also be the whole of Rn, but that is fine. Any vector space is its own subspace. If you think in terms of set theory, any set is a subset of itself. So it can be the whole space, it can be part of the space. Either way, it will be a subspace of Rn. Are we together? Maybe I should put all this together like that. So you have a map T that sends vectors from Rm to Rn. The image will be made up of these vectors from which are in Rn, such that they have a corresponding. So this is an example of an image. This vector here is an image because there's a vector here which is sent to it. Now the vectors that are outside here there's no corresponding vector here that will be sent to them. So if I have another vector here, let's call it U, which is outside the shaded region, then it has no corresponding element from Rm rather, which is sent to it. So this one, it has no pre-image under this map. We will see some examples. Is that clear? So this is explains everything that we have just talked about. It just repeats what we were saying. So I don't know if anyone is writing notes or we can move on.
I have a question. How will we know if RM is mapped fully to Rn or partially? How will you know?
We will do some examples, you will see. There are ways to
Okay.
tell. So here is an example. We have this map. This one is from R3 to R4. So it picks X, Y, Z and sends it to this vector in R4, where the first element is X minus Y, second one is 3Z, the third one is Y plus Z, and the fourth one is 0. So any element in the image will look like this, right? You can see that. So it turns out that if you look at this carefully, you see that you can write it as a linear combination of these three vectors. If you pick X, maybe I should go to the board again. So hopefully you've captured this, but we can go to the board now.
It's the same one we did earlier.
You saying? Okay. I did not get the question, but I can always ask again later. So X, Y, Z, we are saying it will be sent to X minus Y. We have 3Z. And we have Y plus Z. We have 0. So if you check carefully, you can observe that this vector here, because anything in the image will look like this, you can express it as a linear combination of some vectors. So we first of all pick X, and throughout we look for the presence or absence of X. Here X appears with the coefficient 1, so I can put 1. Here it does not appear. In the second slot, it doesn't appear. In the third slot, it doesn't appear. And in the final slot also, it does not feature. I'll leave it out. Then the next thing I look at is Y. In the first slot, Y appears with -1. It does not appear in the second slot. It appears in the third with 1, coefficient 1. We keep on going on. Now we go to Z. Does not appear in the first slot, so I have 0. It appears with coefficient 3 in the second slot, 1 in the third slot, and 0 in the last slot. I think there are some people trying to join.
Excuse me, sir.
Yes.
So when we are finding the matrix of the linear transformation, would it be easier to use the method that you just used? That is finding the coefficients of each of the dimensions, and then like combining those columns into a matrix after you are done. That is instead of using the orthogonal basis.
I'm not using any orthogonal basis now.
Yes, I understand.
Mhm.
But if you were to combine these columns here, you'd still get the matrix of transformation, matrix of the linear transformation. I think it would be much easier than using the other method.
I'm not interested in the matrix now.
I understand that.
So just be patient.
Okay.
Yes. There are very many different ways you can do this. So this is just one of them. Unfortunately, you can't do all of them at the same time. So here we are just working with the intuition first. Let's stick to the intuition. So if you look at this, you can write it as a linear combination of these three. Okay. So any element, because any vector in the image can be written like this, then this completely describes the image. So these three vectors, the span of these three vectors is the image. So if you want to get anything in the image, just get a linear combination of these three vectors. Now, if you look at these three vectors, I don't know if I continued with them in the next. Let's go back to the board. So now, if you look at these three vectors, they will form a set of linearly independent vectors. So I can call this vector V1 so that I don't keep writing them. I can call this second one V2. I can call the third one V3. So we'll have three vectors, V1, V2, and V3. Now, if you look carefully, you can check later. These three vectors are linearly independent. I think they are. If they are not, you can verify, but they are linearly independent. So the image of T can simply be described as the set of all linear combinations of these three vectors, but that is precisely what we call the span of the three vectors. So this is a span of. So now I can fully describe the image as a span of these three vectors. So I know very well the images are in R4. images are in R4. So I know that R4 is a 4-dimensional space. The 4-dimensional space. So if I have three vectors cannot span the whole of the 4-dimensional space. I need a total of 4 linearly independent vectors to span the whole of R4. So what does that mean? That my map is not surjective because the image cannot be the whole of R4. So T is not surjective. Are we together? Up to that point. So you can even confirm that it's not surjective because if you are, so what I mean is this. Our map picks vectors from R3 and sends them to R4. So we'll just pretend that this is R4. This is the bag that contains all the vectors in R4. So the claim is that the image, so the map is T. The image we are claiming is not the whole of R4. Why? Because R4 is 4-dimensional, but the image is spanned by only 3 vectors. So it means it can't be surjective. So one way to double check that is to find vectors in R4 which are not in the image. So look for vectors in R4 which cannot be written as a linear combination of these 3 vectors. One simple vector you can check is this one. If you check 0, 0, 0, 1, cannot be written. There's no way you can write this vector as a linear combination of these 3. The reason for that is that the last value in all the 3 vectors is 0. Doesn't matter what you do or how you combine them, you will never get 1 in the 4th slot. So here we have found an example of a vector in R4 which is not, it is not in the image of our linear transformation. So this again shows you that the map is not surjective. But you didn't have to do that just using the knowledge of the basis and knowing the dimension of R4. You can tell that the image is not the whole of R4. It is only a 3-dimensional subspace of R4, and that subspace is the span of these 3 vectors. Is that making sense? We learned about the span of vectors earlier. That's why I keep telling you, you need to keep track of everything we do because everything keeps reappearing. So there is an example where we've been able to describe the image of a linear transformation and shown that it is not surjective. So this is just repeating what we have said, and this one gives you another whole bunch of vectors which are not in the image. As long as T is a real number, not equal to 0. As long as T is not equal to 0, then this vector will not be in the span of these 3. Are we together? So here is some 2 exercises. Can you try to figure out the images of these maps and determine whether the maps are surjective? So find the images. In other words, describe the image. You don't have to get you can say, for instance, this image is a linear combination of the following set of vectors, or is a span of the following set of vectors. Try to figure that out, then that should not take you too long. They are simple examples. So another 5 minutes. I'll let you try that first, then we shall solve them on the board. Umemaliza? Ama bado?
Bado.
Okay. I can get myself a cup of tea while you are fighting out these two.
Okay.
Okay, means you're finished or you're
No, go get some tea.
okay. doesn't move. Sasa mmemaliza? Ama bado?
We are done, but unsure of our answers.
Doubting. Okay, we can go over the answer. So the first one, what it does, it picks a vector from R3 and sends it to a vector in R2, I think, x0. So your image is a vector in R2. So image will simply be all vectors that look like this, where x is a real number and the second component is 0. So you can write all of them as a multiple of the vector 1, 0. So the image is simply all the image of this map. If you call this map T, maybe I need to make this pen bigger. Let's try again. I think that's better. So if you call this map T, then we can say that the image of T will be equal to the span of just one vector, 0, 1. So if you think of it geometrically, this is just the x-axis. Remember earlier on, we said that the subspaces of R2 are the lines that go through the origin. In particular, this is just the x-axis, all the multiples of this unit vector in the direction of x-axis. So clearly T is not surjective because the x-axis is not the whole of R2. This map is from R3 and it goes to R2. So this is clearly not surjective because you have certain, there are a lot of vectors that won't appear here. If you were to draw this in geometrically, then it would just be this red line, the x-axis. The rest of the vectors are not in the image. It's only the x-axis. Is that the same answer you got?
No.
What did you get?
I assume now that we are using T has the vectors x, y, and z, and we have x and 0, I got my answer as x into 1, 0, 0. So I had like 3 vectors for x. So where umeandika mbili?
So now you have to be very careful. The image is made up of elements in R2. R2 contains vectors that have only two components. One component in the X position and one component in the R2 cannot have a third vector, a third component rather. And then you can't add another 0 because you already have the image. The image is here. The image of this element is given to you as X0. So don't change this image. Use it exactly as it is.
Okay, but how comes we haven't looked for Y and for now that Y and Z are zeros? Okay. Okay.
It is
Now I
Z in
understand.
R2.
No, now I've understood. Yeah.
Yeah. So it's only X and Y in R2. They're the only two coordinates. Anyone else with a question on this?
I have a question. Why are you saying it's only X and Y, and in this case it's only X?
There's a Y
Because
coordinate which is 0. There are two. Okay, if I don't say X and Y, maybe let me say there are two coordinates here. Is that better?
Yes, yeah, no, that makes sense.
Yes.
Okay.
There are two coordinates here. There's a 0 and there's an X. 0 is for the Y coordinate, X is for the X coordinate. So the next one was from R3. Let's go back to blue, I think. So from R3, again, we pick, it was taking a vector X, Y, Z. And sending us to, I think we have X plus 2Y. Then 2X plus Z. So again, you can split this as follows. This vector on this side, you can split it as, because these are the images, all the images look like this. So you figure out, how do I write them in general? This is a plus. You can write them in general as a linear combinations like this. First of all, pick X. X has a coordinate 1 here and a coordinate 2, the second slot. Y has a coordinate, what? It has coordinate 2 here. And it has coordinate 0, the second slot. Then plus Z has coordinate 0 in the first slot, and it has coordinate 1 in the second slot. So any element in the image can be written as a linear combination of these three vectors. So if we call our map T again, we don't have to be using the letter T. You can use any other letter you wish, but T is sort of a tradition, but you don't have to use T. So here we are interested in the image of T. And we'll say that the image of T is a span of these three vectors. Zero. This is 0. And then the third vector is 0, 1. So these three vectors will span the image of T. So the question is, we want to check, is this map surjective? Can the image itself is R2? Remember, we are moving from R3. R2. So the question is this surjective? In other words, is this image equal, the elements in the image, will they cover the whole of R2? So if you look carefully, what can we say about this set of vectors? We know the dimension of R2, and we have 3 vectors from R2. What does that mean? It means this set of vectors must be linearly dependent, right? So it means we can throw away some of them. So for instance, if I pick this last vector on this side, 1, 2, is linearly dependent on the other 2 vectors. So I really don't need it. I can write it as a half multiplied by 2, 0 plus what else? 2 multiplied by 1, 0. So this vector is redundant because I can write it as a linear combination of these 2. So I can throw this away without producing, or rather changing the span of this set. So I can make the following claim that this can also be written as a span. I throw away this vector that is linearly dependent, because if I need it, I can always recover it using the other 2 vectors, 2, 0 and 0, 1. So these 2 are linearly independent now, these 2 vectors. So it means it's telling me that dimension of the image of T is equal to 2. And we also saw earlier that any 2-dimensional subspace of R2 must be the whole of R2, right? We saw this. So it means, this essentially means that the image of T is the whole of R2. So this map is surjective. In other words, any vector in R2 can be written as a linear combination of these 2 vectors, which are the span of the image. So the image is the whole of R2. Are we together? So this one
Yeah,
now,
so
yes.
so meaning before we always conclude, we should check if we can express the vector first as a linear combination of the other and reduce it. If that is possible, then because
Yeah, you can
before
knock
you
them out
reduced
until you're
it,
left with a set of, pardon?
before we reduced any of these things, it showed that it is not surjective, right? So whatever you're
No.
saying is,
If you, before you reduce it, you can't tell.
yes. So whatever you're saying is, we should always try to reduce our vectors to the smallest values possible, or the simplest way possible, before we conclude if it is
If you are
surjective.
asked to reduce, if you're asked to reduce, you should.
Okay.
Now this is easy to do because you have you're working with a small space, the 2-dimensional space. But if you have larger vectors, you need a more elaborate way of doing this, or of reducing them. You'd have to apply some row reduction. So like for instance, in this case, you could write out the vectors as a matrix. So the first 1, 2, the second one is 2, 0, and last one is 0, 1. So you reduce this to just echelon form is sufficient. If you wish to go further, you can go to reduced echelon form. So if you reduce this to echelon form, the first step will make this a 0, right? So multiply this by -2 and add it to this. So you'll end up with 0 minus 2. This other one is already 0, 1. So the next step, you can try it yourself. 1, 2 is fine. The next step will be 0. You turn this into a 1 if you wish, although you can just switch these two. And then after you switch the two and you want to make the last, this bit 0, both of them will become 0. Right? So these two form a basis. 1, 2, and 0, 1. So again, the basis is not unique. This one, we could easily figure it out. So the other way you could have done this is you could also write 0, 1 as a linear combination of the other two. Then you kick out 0, 1. Then you're left with these two, 1, 2, and 2, 0. 2, 0 can also be simplified to 1, 0 because since the span is made up of linear combinations, even if you turn this into 1, 0, you can always get 2, 0 by multiplying 1, 0 by 2. So any one of these two can be thrown out. So this has shown that because we end up with the two vectors now. This first one, which is 1, 2, and then the other one, which was. So these become the basis. So the Gauss elimination has given us a different basis, but still spans the same space. These two they're the basis for the same space. And how you obtain the other basis that you have also is now 1, 2, and 0, 1. That's that one we have. Then I think you also have 1, 2, and 2, 0. So we have out of these, there are many. These are not the only ones. You can actually have infinitely many bases. By just getting multiples of this, you can get other basis vectors. So the last one is what? 1, 2, and 2, 0, because you can write 0, 1 as a linear combination of these two. You can sit down and try to figure that out, you will see. So 1, 2, and 2, 0. So all these are different bases, but all of them have exactly two vectors. And therefore the image of T doesn't change too. And you don't need to find all of them, you just need to find one basis. Once you find one basis, that's enough. Because any other basis you find will not be bigger, it won't be smaller. It will just have exactly two vectors. So I need to go back to the slides. So there's a more general way of finding the image, the spanning set for an image. I've given you a hint using this last example. Hopefully, if we don't find time today, maybe next time we can do some examples. But I'd like to keep the next class as the last one for theoretical work. From after next week, I think everything we do should be application. So the next set that we need to look at is the kernel of a linear transformation. So this is just, if you have a vector linear transformation from Rm to Rn, the kernel is just a set of all vectors from the domain, which are mapped onto the zero vector in the codomain. In this case, Rn is a codomain. I will try to illustrate this with some diagram. So if I have a map from the vector space Rm and I send vectors to Rn, so I'll call my map T. Again, I will use the bugs. So this is Rm and this is Rn. So remember, there's always a zero vector. I'll call it, maybe I'll put a bar there. When writing by hand, it's difficult to differentiate between bold and normal font. So on this other side, you can have a set of vectors. Let's shade them out. And each of these vectors, T will send them to 0. Any one of these vectors, T sends them to 0. Right? So this set of vectors here that are sent from Rm to 0, the 0 vector in Rn, is what we call the kernel. So this small shaded space is a kernel of the linear transformation. So if you are to write it out in set notation, the kernel of the map T is simply the set of all vectors in Rm. Let's call it Rm, such that the image of V is the 0 vector. Now this 0 vector is a 0 vector in Rn. So that's basically the kernel. This is a set of all vectors here, which are sent to the 0 vector. Yeah.
I have a question. When you say that the set of vectors that are sent to the 0, does it mean that all the vectors that when they reach this other side of the space Rn, that they are 0, that their answers are 0, or?
You say the image is 0. So you see what happens is it's the same thing you do if you buy maize from a shop, you can roast it. So your function here is roasting. So you roast it and get something else. Now you have roast maize, right? So we are roasting each of these, and anytime we roast them, we get the 0 vector. So our roasting is this function T. So you have an input, the input goes through some process, and then there's an output. In this case, all of these, when they go through that process, the output is the 0 vector. You must have learned about functions.
Yes.
At some point. It's the same thing.
Naona tunaidenote na hiyo kitu hapo juu. If it's just a normal 0, if our result is 0, why does he?
0 is not a number, 0 is a vector. So for instance, if this is R2, when I say 0, when I say the 0 vector, I mean this. So this is a 0 vector. So this is what we mean by the 0 vector. I put the bar so that we know it's a vector. Again, you must have learned about vectors at some point.
Yes, oh yes, okay.
A lot of these things are not entirely new. That's why I'm not going down to the basics. If you did any maths in undergraduate, this must have been part of it. What I'll do, I'll share a textbook which now has more detail. The problem is the textbooks cannot simplify things. So that means you also, if you're going to look at a textbook, you have to have more time to read. I'll share a textbook on linear algebra where you can now read everything from scratch. But although you already have one, it's just that the other one that you have is it's a bit advanced. Doesn't start from scratch.
So I have a question. So in this process, to me your example ya maize vile umesema. So when we take the maize before it goes through all that process for it to become roasted, So the actual maze that hasn't undergone any of these processes, which is T in our situation, is the kernel of T. The maze
not,
that is not roasted at all.
T is the oven.
Yes.
That's why you roast the maize.
Yes.
So the maize is here.
Yes.
You roast it using T.
Yes.
You get the roast maize here.
0, which is our 0 vector now. Right?
What is the question?
My question is, the maize, before it gets roasted, in our situation as an example, that is the kernel of T now. That is called,
Oh, yes. You mean not all of it, part of it. There's the other ones that will be roasted, but they will not go to 0. There will be something else after being roasted. So only the ones that go to 0.
That is what now we call the kernel of the T.
Yes, and you can see where I have pay attention to the diagram.
Okay.
This subset is in RM. This map takes elements from here to here. So pay attention to the location. This location is in this set. This one is in this set.
Okay.
I think there's someone trying to join me. Let's see where they are. Looks like the number of students are now stabilized at around 42. When we started, we were around 50. Maybe some people have dropped out. So that's the definition of a kernel. It's important that you understand the definition so that anytime we use it, it makes sense. So here is an example of a map. This one is from R2 to R2. It picks X, Y, and sends it to X0. So if you pick any vector that is of this form from R2, where the first component is 0 and the second one is any real number, Y, then the image of any such vector will be the 0 vector, right? So these would be the vectors now that form your kernel, because all vectors of this form, including the 0 vector, will be sent to 0. So the kernel of this map is a set. In this case, it's just the Y. Since we're in a 2-dimensional space, it's just the Y-axis. The whole of the Y-axis will be sent to 0 under this map. And this one gives you the span. So the kernel is simply the linear, all the multiples of this unit vector in the direction of the Y-axis. If you're working in 2 dimensions, you have the luxury of getting the geometric interpretation. If you go beyond 3, then the geometric interpretation may not be so obvious. So that is the kernel. We've been able to find the kernel. There's a more systematic way of finding the kernel, but this one was to use a simple example and to show how you can quickly find the kernel if you have a simple example. So here is a second one. It's a map from R3 to itself, R3 to R3. And if you look at this carefully, the only vector that will be mapped onto a 0 vector is where all the components are 0. If any one of these components is not 0, then the image will not be the 0 vector. So this kernel is interesting because it contains only the 0 vector. So no other vector is mapped to 0 except the 0 vector. This has some significance. I think there's a theorem later we'll look at which will tell you whether a map is 1-to-1 or not? One-to-one, injective, the same thing. It's actually here. So this one says the following: if you have a linear transformation, it will be injective if and only if its kernel consists of just the zero vector. Injective for functions, I think you have done that at some point. Injective means one-to-one. If you don't remember, note it down and try to do some research on what is a one-to-one function, or you may have to go back and revise. If after revision you are not able to get it, you can come back and ask.
Excuse me.
Yes.
Can you use a layman's language on the example?
So the other thing I will say, we are not trying to make you a layman.
No,
Or I don't
you
know,
see
should
the
I
way
say
you used,
laywoman?
no, the way you
So-
used the maize example,
so-
it was easier. Kwa hizi example nimepotea
So
kidogo.
the thing is, when you come to do a master's, there is an understanding that you have some basic degree. So we want to build on that, not to go back to the basic degree again. That's the whole point of the master's, to build on that. So I will try to keep it at a level where it builds on what you already have. Because you have to push yourself to that level. So we'll do an example of but like I said, we just use the previous examples that we covered. This one is easy. We can go back to need something more interesting. Oh, this one again will be injective. So I want one that is not injective. Maybe we will have to create one. But please, the point of all this is not to make you a layman. You are supposed to be a data scientist. And data scientist now you have to work at a higher level. So get the layman bit out of your mind. We want you to be the guru.
Okay.
So what do I let me create an example. So let's pick some examples, say from R3 to pick one that's easy to work on. This might be it's okay. I think this is fine. Let's pick R3 to R4. And let's define the map as follows. It will pick some vector. XYZ, and it will send it to, so let's say X minus Y and Y, not one, X minus Y, and I have Y. R4, so I can put Z here as a third component. Let me write this a little better. I have Y here and I have Z. No, this is bad. Let's make, I want the kernel to be bigger than just the zero vector. So I want 0 here. So now, for me to get the kernel for this map, I need to find any vector from in R3, all the vectors in R3, which are mapped to. We need all the vectors in R3 such that the image is the 0 vector in R4, right? So I want all the vectors which are mapped onto 0. But I know what the map does. This is what it does to any vector in R3. It turns it into a 4-dimensional vector. So to find the values of X, Y, and Z, which will be mapped onto 0, I simply need to equate this image send this to, let me make this a little more interesting. So instead of just Y here, I will have Y plus Z, and also here Y plus Z. Okay, so I want all this to be such that everything goes to 0. So if I need to find values of X, Y, and Z, which will satisfy this condition. If I find those values, then I'll be able to construct my kernel, all the vectors that are mapped onto 0. So can you find these values, X, Y, and Z, that satisfy this? So what you end up trying to solve a system of linear equations, that is X minus Y is equal to 0. So it's a system of linear equations in 3 variables, Y plus Z is equal to 0. So if you find a solution to this, then you will have found a kernel. Maybe we should proceed and complete this. So as usual, we set up the augmented matrix, 1, minus 1, 0. This is 0. Then we have 0, 1, 1. So we can, this is luckily for us, it's already in echelon form. We just need to put it into reduced echelon form. So the next step will be what? We'll use back substitution because the last row is fine. Then I simply add, right? Is that correct? So what do I have now? I have a new system, which is X. The others have coefficient 0. Then I have Y plus Z is equal to 0.
Made a mistake on the first row is.
I made a mistake. Eh? Oh yeah, we were adding. So this is 1. Thank you. That's fine now.
Yeah.
So this then changes to X plus Z. I think now we are fine. So it means I have 2 basic variables, X and Y. I have 1 free variable Z. I need to write the basic variables in terms of the free variables. I can set Z to be equal to T because Z is a free variable. Then in that case, my solution will be what? I'm trying to take a shortcut here because you already know how to do this from the previous class. So X will be what? Minus T, right? Y will be minus T as well.
Yeah.
And Z will be T. So this you can write as T is minus 1, minus 1, 0. So any vector of this form, where T is a real number, will be in the kernel. So there's a way you can get all these vectors from the matrix of a linear transformation. I think maybe next time we'll do one such example. So there's a way you can extract them from the matrix of the linear transformation. We'll do that. Or not now. So here I have the kernel. So if I, let's check what happens. If I have, this is 1, not 0. Just hold on. This one is 1. So any multiple of this. So you can say that the kernel of our map T is actually there. It's a span of this, it's a one-dimensional subspace of R3 spanned by this vector 1, -1, -1, and 1. That's the kernel. So any multiple of this vector will be in the kernel. You can check that this vector is actually in the kernel. We are saying X is supposed to be -1 and Y is -1. So -1 minus -1 will give us 0, right? It works. What about Y plus Z? We have -1, Y is -1, and Z is 1. So it is a solution. And any multiple of this vector will still work. So for instance, you can multiply this by 2 and you will see that the resulting vector will be in the kernel. So this gives you the set all the vectors that are in the kernel. This is how you describe them. Or any multiple of this vector is in the kernel. So this forms a basis. It's a one-dimensional subspace of R3. So again, like I said, this requires you to go and sit down and go through this very carefully. There is no shortcut. You have to get rid of the layman mentality. You must work at this level now, because the exam will not go down to the layman level. You must work at this level.
Just a question, sorry.
Mm.
Go up a bit, songa juu kidogo. Hapo. You see where when we are setting the matrix into the augmented form, what have you added to get rid of the negative so that we get 0, 1, 0, 1?
So you have to sit down and reduce. This is a system of linear equations. This is what we did last time.
Yes.
So just apply the Gauss-Jordan elimination and put this matrix, coefficient matrix, in reduced echelon form. You will get this.
Okay.
So what I can do, this what do you call it? This board that I'm using is part of what do you call it? Pencil app. You can actually, I can prepare a classroom in here where you can have meetings, because maybe you don't have a place to discuss. If you have some discussion groups and you wish to discuss some things, it's very useful to work with the others. So if I set up a classroom in this pencil app, you can join in anytime and have your discussion. You can set up a video call. It can, or maybe you may have your own. You may have your own boards, because there are many applications which do this these days. That's another thing you can do as a group, and try to go through some of these problems. So this one is simply row reduction. And that's why I keep saying anything we do, please make sure you revise it, because we shall need it as we go along. So I can't keep repeating. Otherwise, we will not finish what we are supposed to finish. You must take time and go through the previous work carefully. So when you watch the videos, or if you do watch the videos, you make sure you have a pen and paper and do the calculations by hand. That's the only way you learn. And also that's the only way you will have more questions to ask. So the other thing we are going to look at is composition of linear maps. So do you have a forum where you can do the group meetings, or should I set this one up?
Set it for us.
Okay. So, but I'll need the email addresses. So I think I'll talk to Kibet to arrange to get me all your email addresses. Maybe get a Google sheet and put all of them in there. Then I can invite. I can invite everyone to the class to that classroom. Then I think you can use it. Once you get in, you can create boards. I don't know if anyone has used this app before, but there are tutorials on how to do it, even on YouTube, on how to use it. Called Pencil app. It's a there are some who may have used it before. I don't know if there's anyone here who was in my class in third year. At some point, we used this in one of the third year classes when we were still online. So the good thing is that it's also free. So let's do the final part for today, the composition of functions. So the composition of functions. So how this works is the following. We need two functions. So let's say one function which takes vectors from Rm and sends them to vectors in Rk, where k is an integer. Then I also need a second linear transformation, which now picks up from Rk and sends Rm. So again, there's no special reason why you must use Km and just hold on. I need N, not M again. So then you can get the composition of, and so it will work like this. You get the composition of S and T. This works exactly the same way as composition of functions. So what will happen is that the composition now will pick vectors from Rm and send them to Rn, but through Rk. they will have to go through an intermediate step. This is M. So now this will give you a new map which moves from RM up to Rn. The intermediate step will be RK. So the claim is that this new map is also a linear map. So for now, I will not prove it. You just accept it as it is. So if you get two linear maps, their composition is linear. So you probably did a bit of this in high school when you are getting two different linear transformations in sequence. Maybe you start with a rotation followed by a stretch, or you start with a reflection followed by a rotation. So that's still composition of linear transformations. Those were some of the examples you may have dealt with. There's an example here. So we have two maps. One is from R2 to R2, where XY is sent to 0Y. And the next one is S, which picks up from R2, R3, and sends XY to minus X minus Y 0. So we need to determine the composition of these two maps. What would be the answer? So let's try to do that. So we have two maps. The first one is from, we take T from R2, sends vectors to R2 again. Then you have a vector, the map S, which picks up now from R2. So if you are to go by, in this case, M and K are the same. They are two. They don't have to be, but we have picked them to be the same for this example. So M and K are actually both equal to 2. So S will pick from R2 and take us to R3, I think. Yes. So this is defined as, I think it takes vector XY and it sends this to the vector 0Y. And this one picks a vector XY and sends it to a vector in R3 is minus X. Just picked a simple example so that the calculations are easy. So the aim is to find this composition. So this composition is going to pick, because T is the one that acts first. So it will start from R2 because T acts on R2. And goes to R2. Then S will pick up from R2 and eventually take us all the way to R3. So the new map would be from R2 to R3. So if you want to get, if you want to define this map now, you have to pick a vector in R2 Let's pick a vector in R2. So the first actor is T. What will T do? It will send you to 0y, right? Then S will pick up from there. What does S do? X is 0, so this is just 0. Minus y and 0. So this map ST, S composed with T simply picks xy and sends it to a vector in R3, 0 minus y, 0. So I'll give you an exercise. I want these two matrices, the matrix of T with respect to the standard basis and the matrix of S with respect to the standard basis. I need those two matrices so I can give you some time to compute them. They have easy examples, so you can easily work them out. So I just want the matrix for this T and the matrix for S. Give me those two. And then once you find the matrix for T and S, also find the matrix for this composition of T and S. You have the map here now. Anyone who finds them, you let me know, then we can pick up from there. Have you understood the question? We have three transformations. I want the matrices for each of those three transformations. With respect to the standard basis. Should be done by now. All you're doing is getting the images of a standard basis vectors, so shouldn't take too long. Anyone who has found the matrix for T? Okay, I think maybe Mechoka. Today we didn't take the break. So we'll work them out now. The first thing we do for T, we simply get the standard basis consists of these two vectors, 1, 0. And the second vector is 0, 1. Get the images of this. So to get the matrix for T, what's the image of 1, 0? It will be 0. Is that correct? What's the image of 0, 1? Can anyone hear me?
Yes, we can.
Okay. So the image of 0, 1 will be what?
0, 1.
It said correct. So this is the matrix for T. Usually when we are representing the matrix for linear transformation, we represent it using these square brackets around the linear transformation. Where the basis is known, you could leave it out, but sometimes if you want to specify, you may have to put a subscript here and specify the basis, where the basis will be defined at some point and may be called B. So if you want that done with respect to a given basis, you have to specify it. Ours is done with respect to a standard basis, so we know that already. So we don't include it there. So now we need to get the matrix for S. Again, S is from R2. So our basis to start with will be 1, 0, 1, 0, 1. Start from R2. The image for 1, 0 is what?
-1, 0, 0.
It's -1, -1, 0. Oh, sorry, 0. You're right. I think I'm the one who is tired now. I'll just write it out afresh. -1, 0, and 0. What about the image for 0, 1?
0, -1, 0.
-1, 0. So this is the matrix for S. Now we need the matrix for the composition, S of t. Now S of t also starts from R2. So again, we'll still be getting the images of the basis vectors for R2. So this matrix will be what? So the image of 1, 0 is what? 0, 0, 0, right? What about the image of 0, 1? It will be 0, -1, 0. So you can check that this matrix is equal to it's the same as the product of these two matrices. If we did our work correctly, that should be the case. So this matrix for S multiplied by the matrix for T. Just the same way you have a composition is the same way the matrices are multiplied. Since T acts first, it has to be on the right. 0, 0, 0, 1. So if I know the matrix for the linear transformation of S and that of T, I can get the matrix of a linear transformation of the composition of S and T just by multiplying them in the same order in which they appear in the composition. We can double check if this is correct. I hope we did the correct calculations. So is this 0? And 0, is that correct? This is 0 and -1, which is exactly the same as, turns out to be the matrix we got for the composition of S and T. Is that okay? My handwriting is not the best, so if there's anything that is not clear, you probably have to ask. This is not 0, this is a composition. That sign is for the composition. It's the same sign here. And here as well. So this last bit was, we have confirmed that if you have the composition of two linear transformations, you can get the matrix that represents the composition as a product of the individual matrices of each of the linear maps in the same order in which they appear. Any questions? So what's more interesting now is to look at cases where you have different bases. When you have different bases, you work with coordinates. Even here, you are still working with coordinates. It's just that the coordinates coincide with the vectors because you're working with a standard basis. So the coordinates are just the vectors themselves. But if you are using a different basis, the coordinates will not be the vectors themselves. So like when you're working with the principal components analysis, you usually just changing the basis. You're changing from standard basis to use a different basis. And the new basis that you use is more useful to you. It will not make a lot of sense now, but that's what happens. You will see that when we get to when we start applying. So I think after next week, all our classes will be focused on application, and then you will see some Python now. There are no more questions. Ama mmetoroka wote. I might be talking to myself.
Which scenario will we be working with the coordinates if we have different bases?
I can't explain it in one sentence. It's a whole class in its own.
Okay, so utatufunza hiyo basi.
Yes, we will find a way to simplify it.
Okay, sawa.
Yeah, if we were to do the full linear algebra as it's supposed to be done, we would not be. We probably would be still in one of the earlier chapters because we'll be covering quite a bit of theory. I've tried to make it as I've tried to squeeze out the juice and throw away the pulp so that what we cover will be what we need for the applications. Where we need more, we shall cover them as we go. Like, for instance, we have other decompositions that we need to work on. We have worked only on the eigen decomposition of a matrix, and in particular, the orthogonal decomposition of a symmetric matrix. We still have the QR decomposition, the LU decomposition. We have the non-negative matrix factorization, which is useful for some of the clustering techniques. So we shall try to now use them alongside the applications. Where we need something new, we add it where we are applying it. I will stop recording. So bear with me. I will share I think last week I did not share the slides because I came across some errors. I think while we were in class, I have tried to fix them. The best, I'll just double check them and add a few more things to complement what we have done today. And I will share them.